Friends, welcome to the lecture 41 of Advanced Marine Structures. In this lecture, we are going to learn example on curved sections to locate the shear center. Okay. So, we already studied locating shear center from the first principle. It's a simple exercise provided the section has got at least one axis of symmetry. If axis of symmetry does not exist, then the section will be subject to unsymmetric bending. Then we have got to combine both the problems of unsymmetric bending, locate the UUVV axis, then find the shear center. I will come to that problem slightly later, we will do that. So, in the previous examples we discussed about rectilinear sections like I section, channels, T, etc. In this example, it is quite interesting. We will take a curved section because we are going to slowly understand the analysis and design of curved beams and crane hooks. So, we need to at least examine the curved section for shear center calculations. Let us do that. Okay. We will take, I will call this example 1 for this lecture. Okay, we will talk about curved sections. So, now let us say I have an axis of symmetry of the section. We will mark a curved section symmetric about this axis. So, let us say it has got a center line and that center line is at a distance r from here, and I call this point as O. Okay, this point as O. Let us say it subtends an angle 2 alpha symmetric about the center. So, this angle is alpha. Let us believe the section has got uniform thickness T and the curvature start of this section from the axis of rotation is taken as beta. Okay. So, now obviously being this the axis of symmetry, shear center will lie on this axis. Let us mark the shear center somewhere here. If the force and the reaction pass through the shear center, the section will not be subject to any distinct moment. We call this distance of the shear center from the axis of curvature as E. Okay. So, the question is now I want to find E. The given data for the section are the following: radius of the section, thickness of the section, the included angle and the subtended angle. Let me write it clear or known to me. Okay. So, let us now cut a section which is subtending an angle d theta at theta from here. Well, let us say this is my hatched portion. Okay. Now, the shear stress tau is given by the classical equation V by IT integral y dA. Now, my question of integration is going to be for the element is going to be varying from beta to theta. That is my control, is it not? That is my dA. Look at here, this is my dA, right? That is what I am looking at. So, let me do that, which will be equal to V by IT integral beta to theta, y will be r cos theta and r d theta d theta, t d theta r d theta t will be the area of the hatched portion, which is green in color. This is y bar. So, we can do this. So, the elemental shear stress tau is actually equal to V r square by I sin theta minus sin beta. Am I right? That is my elemental shear stress. Also, friends, we have an interesting relationship here. From this figure, we can say pi by 2 minus beta is alpha. Can I say that? From this figure, from the geometry, this is true. Okay? Having said this, so we said that tau is V r square by I sin theta minus sin beta. Now, I can find the elemental shear force, which is dV, which will be actually tau dA. So, now I can find dV as V r square by I sin theta minus sin beta into r t d theta. So, now this becomes V r cube t by I sin theta minus sin beta of d theta. This is my dV. Now, the moment of this shear force about the center is given by dm. dm will be straight away into r, is not, the distance is r, radius. So, I can say V r cube t by I sin theta minus sin beta d theta multiplied by r. So, this will become V r 4 t by I sin theta minus sin beta into d theta. That is my dm. So, once we obtain the elemental moment, we can find the total moment m, which will be integral of dm varying from beta to pi by 2, 2 times of that. Okay. So, the total moment m is twice of integral beta to pi by 2 dm, which will be twice of integral beta to pi by 2 v r 4 t by I sin theta minus sin beta d theta. So, which will give me m as 2 v r 4 t by I of minus cos theta minus theta sin beta, apply the limits from beta to pi by 2. So, that will give me m as 2 v r 4 t by I. Okay, before that, we also know pi by 2 minus beta is alpha. Can you see this here? Let me use that relationship here. So, now saying that m will now become 2 v r 4 t by I minus cos pi by 2 plus cos beta minus pi by 2 sin beta plus beta sin beta. So, we can say this is 0 and we have cos beta sin beta, right. Now, I can simplify this equation as 2 v r 4 t by I am replacing beta as pi by 2 minus alpha. So, can I write this as cos pi by 2 minus alpha minus pi by 2 sin pi by 2 minus alpha plus pi by 2 minus alpha of sin pi by 2 minus alpha. I am bringing all in terms of alpha. Let me copy this equation to the next screen. So, m was equal to this, which now becomes 2 v r 4 t by I sin alpha minus pi by 2 cos alpha plus pi by 2 minus alpha cos alpha. Okay, which is further simplified as 2 v r 4 t by I sin alpha minus pi by 2 cos alpha plus pi by 2 cos alpha minus alpha cos alpha. So, this goes away, which will now land up as 2 v r 4 t by I sin alpha minus alpha cos alpha. We call equation number 1. It is a very interesting equation which is a classical theory available in the literature for curved sections. Okay. Now, let us take moment about O. This is the figure we have. Let us copy this figure. Okay. We will take moment about O. So, V into E is equal to that moment. So, which I say is equal to 2V R4 T by I sin alpha minus alpha cos alpha. That is what the moment we have here. Okay, I have equated this. So, now I can easily get E as 2 R4 T by I sin alpha minus alpha cos alpha. That is my E. If I know the value of E, I can easily find the shear center, locate the center. So, look at this equation. In this equation, R is a geometric property, T is a section property, alpha is the angle of this curved section subtended the center, 2 alpha rather. Okay. But the question is, how about I? I is the moment of inertia of the whole section, is it not? That is what we understand. It is a segmented section, it is not a full curve, so that we can find I readily. It is a segmented section. So, the problem is how to find this. Let us do that. Now, the issue is to find the moment of inertia I of the segment. Okay. So, let us draw this figure again. I will take this figure again. Okay. We know I is y square dA and I want to integrate it for the entire section. So, when I integrate, I can do this as integration of beta to pi by 2 and 2 times of this. Y we already have with us, it is r cos theta, am I right? Look at this figure, r cos theta will be the y value, okay. That is this value. This is r, okay, and this value, r cos theta, is it not? Okay. So, r cos theta the whole square and dA is r d theta into t, am I right? So, now let us simplify this. So, 2 r cube t integral beta to pi by 2 cos square theta d theta. We know from trigonometry that cos 2 theta is 2 cos square theta minus 1. So, hence cos square theta is 1 plus cos 2 theta by 2. So, substituting I is 2 r cube t by twice beta pi by 2 1 plus cos 2 theta d theta. Okay. So, I is r cube t integral beta pi by 2 1 plus cos 2 theta d theta, which is r cube t theta plus sin 2 theta by 2 beta 2 pi by 2. Which is r cube t pi by 2 minus beta plus sin 2 pi by 2 by 2 minus sin 2 beta by 2. Okay. We know already pi by 2 minus beta is alpha, is it not? We already have it here, see here. Hence, I will now become r cube t, say pi by 2 minus beta. So, this becomes 0, half of 0 minus half of sine twice of pi by 2 minus alpha. Can I say that? So, this is closed. So, now I can say I is r cube t. So, look at this figure. So, this becomes alpha minus, this is half of sine 2 theta. So, 2 sin theta cos theta. So, half of 2 sine pi by 2 minus alpha cos pi by 2 minus alpha. Can I write like this? This is, argument is 2 theta, let us say sin 2 theta is 2 sin theta cos theta. That is what I am writing. Okay. So, this 2 goes away now, which will become r cube t alpha minus cos alpha sin alpha. So, this is equation number 2. So, now E is 2 r 4 t by I sin alpha minus alpha cos alpha. That is what we written here. 2 r 4 t by I sin alpha minus alpha cos alpha. So, now therefore, substituting E will become 2 r 4 t by r cube t sin alpha minus alpha cos alpha by alpha minus sin alpha cos alpha. Okay. So, which will now become 2r times of sin alpha minus alpha cos alpha by alpha minus sin alpha cos alpha. That is my E. So, we have all the values. So, geometric parameters, I can find E. Now, I can locate the shear center for a given geometry. So, as a small example, Let us copy this figure. Somewhere, see this figure. Okay. So, let us say let R be 600 mm, okay, alpha or 2 alpha be 60 degrees, find E. So, E is straight away 2R times of sin alpha minus alpha cos alpha by alpha minus sin alpha cos alpha. You can compute this, mark the value, and E will be maybe x millimeters. Okay. So, friends, it is very simple that this particular numerical example explains how to compute the shear center for a curved section as you see here. Okay. We will do one more example. But a slightly a tricky section. Let us see how we handle this section. Okay. Locate the shear center of the section shown. Okay. So, section we have. Okay. Let us mark certain dimensions of this section. Of course, we can locate there is an axis of symmetry for the section. The section has uniform thickness as T. Let us mark the center line of the section for our calculation purposes. And we mark this dimension as B1, and this dimension as B. And this radius as R. We will say the shear center is located somewhere here, and this is at an eccentricity E from here. Let us mark the shear flow we call this arm as V5, this as V4, this as V3, this as V2, and this as V1, this as V1. Okay. So, from this figure we can easily say by symmetry V1 will be same as V5. Further, V2 will be same as V4. Okay. Let us cut a section at Z from here let the thickness of the strip be dz. This is what we hatch. We want to find the CG of this, okay, from here, axis of symmetry. From the figure, you can always write this value as R plus B1 minus Z by 2. Can you say that? Can I say that? So, now I can find V1. V1 will be the force in the vertical arm, which will be integrated from 0 to B1 V by IT A y bar of t. So, A will be T into Z and dA will be T into dz and y bar will be R plus B1 minus Z by 2. We can substitute this. So, V1 is going to be integral 0 to B1 V by IT Tz R plus B1 minus Z by 2 of T dz. Let me rub this. So, we can straight away say it is Vt by I now integral 0 to B1 R plus B1 minus Z by 2 of Z dz which can be Vt by I R B1 square by 2 plus B1 square by 2 minus B1 cube by 6 after substituting the limits, which becomes Vt by I of R B1 square by 2 plus B1 cube by 3. This is my V1 is equation 1. Okay, friends. So, we will continue this problem in the next lecture, but I want you to do a small homework on this. I want you to find V2 and now we have a curved section, we can find V3 also. So, try to do this exercise, then we will recollect it how we are able to do it. Okay? I leave a small gap here intentionally, so that I want you to practice this, okay, and try to do for V2, then V3 and so on. Thank you very much and have a good day. Bye.